Hello there, and welcome to the Sleepy Library. Tonight, we are going to take a slow, peaceful journey across the vastness of space to visit our closest galactic neighbor, a magnificent island of stars called the Andromeda Galaxy. As you settle into your pillow and feel the weight of the day begin to lift from your shoulders, let yourself drift with me through the velvet darkness of space, where ancient light tells stories that have been traveling for millions of years just to reach your eyes tonight. The Andromeda Galaxy hangs in the night sky like a distant dream, a soft smudge of light that has captivated human imagination for more than 1,000 years. It is the most distant object you can see with your unaided eyes, a beacon shining across 2.5 million light-years of emptiness. When you look up at Andromeda on a clear autumn night, the photons landing on your retina began their journey long before humans walked upright, before mammoths roamed the earth, before our ancestors even imagined gazing at the stars. You are literally seeing into the deep past, watching light that has traveled uninterrupted through the cosmic ocean, carrying with it the secrets of a galaxy so vast it contains more than 1 trillion individual stars. Close your eyes for a moment and picture this. Imagine standing in a dark field on a crisp October evening, far from city lights, where the Milky Way stretches overhead like a river of cream. Now, find the constellation Cassiopeia, that distinctive shape like the letter M or W, depending on the season, made of 5 bright stars forming a celestial throne. From Cassiopeia's brightest star, let your gaze drift southward, and there you will find it, a faint, oval smudge, barely noticeable at first, but unmistakably there. That gentle glow is not a cloud. It is not a trick of your eyes. It is an entire galaxy, containing hundreds of billions of suns, each potentially surrounded by planets, moons, asteroids, and comets. It is a cosmic metropolis of unimaginable scale, and tonight, it is waiting for you to explore it. Andromeda is the name of a constellation located in the northern sky. It lies close to the constellations Cassiopeia, Cepheus, and Perseus. Within the Andromeda constellation is the Andromeda Galaxy, one of the largest and closest galaxies to the Milky Way. Because of its size and proximity, it is an important reference object in astronomical studies and observations. The Andromeda Galaxy, also known by its catalogue designation Messier 31, or simply M31, stretches across the sky with such grandeur that if our eyes could see all its faint outer regions, it would appear 6 times wider than the full moon. Think about that for a moment. 6 full moons lined up side by side. The galaxy is so large that even traveling at the speed of light, it would take 220,000 years to cross from one side to the other. That is more than twice the diameter of our own Milky Way. To put this in perspective that makes it easier to grasp, if the Milky Way were the size of the United States, Andromeda would stretch from the Atlantic Ocean all the way past Hawaii and halfway across the Pacific. But Andromeda is not just larger than our galaxy, it is also more populous. While our Milky Way contains somewhere between 200 billion and 400 billion stars, current estimates suggest Andromeda holds approximately 1 trillion stars. 1 million individual points of light, each one a nuclear furnace fusing hydrogen into helium. Each one potentially warming worlds we will never see, never visit, never know. Some of those stars are young and blue, burning hot and fierce, with lifetimes measured in mere millions of years. Others are ancient red giants, swollen and cool in the twilight of their existence. Still others are dim yellow stars like our Sun, steadily burning through their fuel over billions of years, perhaps hosting planets where, on this very night, beings might be looking back across the void toward the Milky Way, wondering if they are alone. Let us drift back through time, following the thread of human discovery. The Andromeda galaxy was first recorded by a Persian astronomer named Abd al-Rahman al-Sufi in the year 964. In his masterwork, The Book of Fixed Stars, al-Sufi described what he called a small cloud in the constellation Andromeda. For centuries, observers noticed this mysterious patch of light, but could not understand what it truly was. They called it a nebula, from the Latin word for cloud, assuming it was nothing more than a fuzzy mass of gas within our own stellar neighborhood. How wrong they were, and how magnificent that wrongness turned out to be. In 1612, German astronomer Simon Marius turned his telescope toward this peculiar object and became the first person to describe it in detail through the lens of magnification. He compared it to the light of a candle shining through horn, a translucent, glowing presence that defied easy categorization. But still, no one understood its true nature. The mystery deepened. Was it a cloud of glowing gas? A cluster of unresolved stars? Something else entirely? The great debate about the nature of these spiral nebulae continued into the early 20th century. In 1920, two American astronomers, Harlow Shapley and Heber Curtis, engaged in what became known as the Great Debate. Shapley argued that these nebulae, including Andromeda, were relatively small objects within our own galaxy. Curtis, however, proposed something far more radical. He suggested that Andromeda and similar objects were separate galaxies, island universes in their own right, lying at tremendous distances beyond the boundaries of the Milky Way. The universe, Curtis claimed, was far vaster than anyone had imagined. Our galaxy was not the entirety of creation, but merely one of countless galaxies scattered through infinite space. The debate was settled in 1925 by Edwin Hubble, the astronomer for whom the space telescope would later be named. Using the 100-inch Hooker telescope at Mount Wilson Observatory, Hubble identified a special kind of variable star within Andromeda called a Cepheid variable. These remarkable stars pulse with predictable regularity, and their period of pulsation directly correlates to their intrinsic brightness. By comparing how bright they appear to how bright they actually are, astronomers can calculate their distance with remarkable precision. Hubble's calculations revealed that Andromeda was not merely outside our galaxy, but staggeringly far away, approximately 2.5 million light-years distant. This single discovery fundamentally transformed our understanding of the cosmos. The universe, in an instant, became almost incomprehensibly larger. Now let your mind wander to the structure of this magnificent galaxy. Like our own Milky Way, Andromeda is a spiral galaxy, a cosmic pinwheel of stars, gas, and dust, rotating around a bright central core. When we observe Andromeda from Earth, we see it tilted at an angle, not face-on, but rather edge-on, which makes studying its spiral arms somewhat challenging. Imagine trying to admire an ornate ceiling painting while lying directly beneath it, versus seeing it from the doorway. The perspective matters enormously. Despite this viewing challenge, astronomers have identified at least two major spiral arms winding outward from Andromeda's center, traced by bright regions where massive young stars are being born within clouds of hydrogen gas. These spiral arms are not solid structures. They are density waves, regions where stars and gas temporarily crowd together as they orbit the galactic center. Think of them like traffic jams on a cosmic highway. The stars move through the arms rather than with them, compressing and bunching up as they pass through these denser regions. In those compressed zones, gas clouds collide and collapse, triggering bursts of star formation that light up the spiral arms with the brilliant blue-white glow of newborn stars. Between the arms lie quieter regions, darker lanes where fewer stars shine and where the density is lower. The entire galaxy rotates, not as a solid wheel, but as a fluid differential system, where the inner regions spin faster than the outer reaches. At a radius of about 33,000 light-years from its center, Andromeda's rotational velocity peaks at approximately 250 kilometers per second, or about 155 miles per second. That is fast enough to circle the Earth in about 2.5 minutes. At the very heart of Andromeda lies something even more remarkable: a supermassive black hole. This invisible giant, designated M31 star, weighs as much as 140 million suns, all compressed into a region of space smaller than our solar system. Black holes are regions where gravity is so intense that not even light can escape. They form when massive amounts of matter collapse into an infinitesimally small point called a singularity, warping the fabric of space-time itself into an inescapable gravitational well. The supermassive black hole at Andromeda's core is not actively feeding right now. It sits relatively quiet, not consuming vast quantities of gas and dust, not blazing as a brilliant quasar. Instead, it slumbers peacefully, held in check by the delicate balance between available fuel and the forces at play in the galactic center. But Andromeda's core holds an additional mystery, one that puzzled astronomers for years. When the Hubble Space Telescope peered into the galaxy's nucleus with unprecedented clarity, it revealed not one, but two bright concentrations of light, separated by only 4.9 light-years. The brighter of these, designated P1, is actually offset from the true center of the galaxy. The dimmer concentration, P2, marks the actual center and contains the supermassive black hole. Surrounding this black hole is a compact disk of hot, young blue stars that orbit at incredible speeds, completing circuits in roughly 100 years while traveling at velocities of over 2 million miles per hour. These stars could circle the Earth in less than 1 minute. They race around the black hole so quickly that astronomers initially struggled to explain how they could form in such a hostile environment. The tidal forces near a supermassive black hole should tear apart gas clouds before they can collapse to form stars. Yet here they are, more than 400 blue stars, estimated to be only about 200 million years old, orbiting in a thin disk barely 1 light-year across. The current theory suggests that this peculiar disk of stars may have formed from a previous merger between supermassive black holes. When two galaxies collide, their central black holes eventually spiral toward each other, releasing powerful gravitational waves as they merge. This merger can kick the resulting black hole, causing it to recoil like a rifle firing a bullet. The recoil can then perturb the orbits of nearby stars, stretching them into eccentric, elongated paths. In Andromeda's case, this gravitational kick may have sculpted the unusual structure we observe today. The stars in P1 linger at their most distant point from the center, creating a concentration of light that appears brighter than the true nucleus. It is a reminder that galaxies are not static monuments, but dynamic, evolving systems shaped by violent events spanning billions of years. Andromeda is not a solitary traveler through space. It is accompanied by a retinue of smaller satellite galaxies, cosmic attendants bound to it by gravity. The two brightest and most easily observable are M32 and M110, both small elliptical galaxies that orbit their giant companion like moons around a planet. M32 is a compact dwarf galaxy, relatively bright and easy to spot in even modest telescopes, located about half a degree south of Andromeda's core. Despite its small size, containing only about 3 billion solar masses, compared to Andromeda's estimated trillion solar masses, M32 has a dense, bright nucleus that suggests it may once have been much larger. Astronomers believe M32 experienced a close encounter with Andromeda in the past, perhaps plunging directly through the larger galaxy's disk. During this violent interaction, M32 would have lost a significant portion of its mass, stars stripped away by Andromeda's immense tidal forces and scattered into the larger galaxy's halo. This collision also triggered an intense burst of star formation in M32's core, creating the relatively young stellar population we observe there today. M110, the other prominent companion, lies about 1 degree northwest of Andromeda. It is larger and more diffuse than M32, with a lower surface brightness that makes it somewhat harder to see, but still accessible to amateur astronomers with good equipment and dark skies. M110 shows evidence of ongoing interaction with Andromeda, including a dusty lane that suggests recent or continuing star formation. Streams of stars have been identified connecting M110 to Andromeda's halo, further evidence of the gentle gravitational cannibalism taking place. In total, Andromeda has at least 35 known satellite galaxies, though many are extremely faint dwarf galaxies, barely distinguishable from the background. These satellites are not randomly distributed, but appear to lie along a single plane running through Andromeda's center, a surprising arrangement that astronomers are still working to explain. Andromeda has grown to its current magnificent size through a process of galactic consumption, swallowing smaller galaxies over billions of years. Deep surveys of its outer regions have revealed enormous streams and clouds of stars, coherent structures that trace the remnants of smaller galaxies torn apart by Andromeda's gravity. These stellar streams are like archaeological evidence, allowing astronomers to reconstruct the galaxy's violent past. One particularly notable event occurred between 2 billion and 3 billion years ago, when Andromeda underwent a major merger, likely with a galaxy roughly 1/4 its size. This collision was transformative. It formed much of Andromeda's metal-rich galactic halo, including a prominent feature called the Giant Stream. It also created Andromeda's extended thick disk, rejuvenated its thin disk with fresh star formation, and shaped a prominent ring structure approximately 10 kiloparsecs, or roughly 32,000 light-years from the center. During this merger epoch, Andromeda's star formation rate skyrocketed. For roughly 100 million years, burned so brightly, creating so many new stars so rapidly, that it would have qualified as what astronomers call a luminous infrared galaxy. The merger converted vast reservoirs of cool gas into newborn stars at a prodigious rate, lighting up the galaxy like a cosmic fireworks display. Scattered throughout Andromeda are approximately 450 globular clusters, ancient spherical collections of stars that orbit the galaxy like bees around a hive. Globular clusters are among the oldest structures in the universe, containing some of the first stars ever formed, often 10 billion years old or more. They are dense concentrations of hundreds of thousands or even millions of stars, packed into relatively small volumes, typically only tens to hundreds of light years across. Andromeda has far more globular clusters than our Milky Way, which hosts only about 160. This disparity reflects differences in how the two galaxies formed and evolved. Some of Andromeda's globular clusters are extraordinarily dense, among the most tightly packed stellar communities ever observed. The brightest of them, designated G1, is also the most luminous globular cluster in our local group of galaxies. Even at Andromeda's tremendous distance, G1 shines at about magnitude 13.7, faint but theoretically visible to dedicated amateur astronomers with large telescopes under perfect conditions. Within Andromeda's disk, regions of active star formation blaze with the light of newborn stars. One of the most prominent is NGC 206, a massive star-forming region clearly visible in detailed images of the galaxy. NGC 206 glows with the intense blue light of extremely hot young stars called O-type and B-type stars. These stellar giants are among the most massive stars in the universe, burning their nuclear fuel at such prodigious rates that they will exhaust themselves and perish in supernova explosions within just a few million years. They are the fireworks of the cosmos, brilliant and brief. Their intense ultraviolet radiation ionizes the surrounding gas, causing it to glow in beautiful emission nebulae, clouds of hydrogen that shine with the characteristic red color of excited hydrogen atoms. These star-forming regions are laboratories of creation, where the matter from previous generations of stars is recycled into new stellar systems, each potentially forming planets, and perhaps even life. Andromeda also contains dark lanes of dust that trace cooler, denser regions where light is absorbed rather than emitted. These dust lanes are particularly prominent on the northwestern edge of the galaxy's core. Interstellar dust consists of tiny grains, mostly carbon and silicate minerals, created in the outer atmospheres of dying stars and expelled into space by stellar winds and supernova explosions. Though each grain is microscopically small, collectively they can block visible light while allowing infrared radiation to pass through. When astronomers observe Andromeda in infrared wavelengths, using instruments like the Spitzer Space Telescope or the Herschel Space Observatory, the dust lanes light up, revealing the galaxy's skeleton, the underlying structure of cool gas and dust that has not yet collapsed to form stars. These observations have revealed that Andromeda's spiral structure may be transitioning. Rather than distinct spiral arms, Andromeda appears dominated by a large dust ring, a circular structure that wraps around the galaxy's core. This ring may have formed from the gravitational interactions with M32 and other satellite galaxies, which perturb the gas and dust distribution in the galactic disk. Let us talk about distance. The Andromeda galaxy lies approximately 2.5 million light-years from Earth. A light-year is the distance light travels in 1 year, moving at approximately 186,000 miles per second, or about 6 trillion miles. So, Andromeda is about 15 quintillion miles away. That is, a 1 followed by 19 zeros. To put this in perspective, if you were to travel to Andromeda in a modern spacecraft, moving at the speed of the Voyager probes, which are the fastest human-made objects to leave our solar system, at about 38,000 miles per hour, it would take you roughly 43 billion years to get there. That is more than 3 times the current age of the universe. Even traveling at the speed of light, the fastest possible speed allowed by physics, the journey would take 2.5 million years. If you left Earth today at light speed, Andromeda would have moved considerably by the time you arrived, because the galaxy is not standing still. It is moving through space, and specifically, it is moving toward us. Andromeda and the Milky Way are on a collision course. The two galaxies are rushing toward each other at approximately 100 to 140 kilometers per second, or about 62 to 87 miles per second. That might sound incredibly fast, and it is, by everyday standards, fast enough to travel from New York to Los Angeles in less than a minute. But on cosmic scales, it is almost leisurely. Given the enormous distance between the galaxies, this approach velocity means Andromeda and the Milky Way will not collide for billions of years. Recent observations combining data from the Hubble Space Telescope and the Gaia Space Observatory have refined our predictions about this cosmic encounter. For years, astronomers believed a collision was inevitable, predicted to occur in approximately 4 billion years. However, the latest computer simulations, which account for the gravitational influences of other galaxies in the local group, including the Large Magellanic Cloud and the Triangulum Galaxy, suggest the situation is more uncertain. After running 100,000 simulations stretching 10 billion years into the future, researchers found approximately a 50% chance that Andromeda and the Milky Way will actually collide within that time frame. In the other half of the simulations, the two galaxies pass relatively close to each other, their invisible dark matter halos interacting but not merging, before flying apart again and potentially colliding much later, or perhaps continuing an orbital dance for eons. If a collision does occur, it will be one of the most spectacular events imaginable, though calling it a collision is somewhat misleading. When galaxies collide, stars almost never actually hit each other. The distances between stars are so vast relative to their sizes that direct stellar collisions are exceedingly rare. To understand why, consider this analogy. If the Sun were the size of a ping-pong ball, the nearest star, Proxima Centauri, would be a pea about 680 miles away. In Andromeda and the Milky Way, even in their densest regions near the galactic centers, the average distance between stars is still approximately 100 billion miles. That is like placing one ping-pong ball every 2 miles. Thus, when these galaxies merge, the stars will mostly pass by each other like phantoms, barely aware of each other's presence. What will collide are the vast clouds of gas and dust in the galactic disks. When these clouds slam together at high velocity, they will compress and heat up, triggering an explosion of star formation unlike anything either galaxy has experienced in billions of years. New stars will be born by the millions, lighting up the merged system with brilliant blue and white light. Open clusters and massive stars will dot the landscape. Nebulae will glow in reds, blues, and greens. For a few 100 million years, the merged galaxy will become a luminous infrared galaxy, pouring out energy at prodigious rates. The supermassive black holes at the centers of both galaxies will spiral toward each other, eventually merging into a single, even more massive black hole. This merger will release tremendous amounts of energy in the form of gravitational waves, ripples in the fabric of space-time itself that propagate outward at the speed of light. Though we will be long gone by then, advanced civilizations anywhere in the universe with gravitational wave detectors will be able to observe this cosmic event from billions of light years away. The final product of the Andromeda-Milky Way merger will be a giant elliptical galaxy, a smooth, featureless blob of stars with no spiral arms, no distinct structure, just a vast, roughly spherical swarm of stars orbiting a common center. Astronomers have already nicknamed this future galaxy Milkomeda, a portmanteau of Milky Way and Andromeda. Milkomeda will be one of the largest galaxies in the local group, though not quite as large as some of the true galactic giants found in rich galaxy clusters. What will happen to our solar system during this merger? The good news is that the odds of any direct collision are infinitesimally small. Earth, the Sun, and all the planets will almost certainly survive the encounter unscathed. However, the gravitational forces at play during the merger will shuffle stellar orbits like cards in a deck. Computer simulations suggest there is approximately a 50% chance that our solar system will be flung outward, perhaps ending up 3 times farther from the galactic center than we are now. Currently, the Sun resides in a branch of the Milky Way called the Orion Spur, about 26,000 light-years from the galactic center. After the merger, we might find ourselves in the outer suburbs of Milkomeda, roughly 78,000 light-years from the center. There is also a small chance, roughly 12%, that the solar system could be ejected entirely, flung into intergalactic space to wander alone forever. More likely, we will simply settle into a new orbit, continuing to circle the center of the newly merged galaxy, our night sky transformed by the redistribution of stars around us. The sky might be filled with more visible stars, or perhaps fewer, depending on exactly where we end up. The Milky Way's characteristic band of light across the sky would be gone, replaced by a different stellar tapestry. But by the time this happens, Earth will already be uninhabitable. The Sun's gradually increasing luminosity will have boiled away our oceans within about 1 billion years, long before the galaxies collide. Andromeda's chemical composition tells a story of stellar alchemy. The galaxy is rich in heavy elements like carbon, nitrogen, and oxygen, the essential building blocks for planets and life as we know it. These elements were not present at the beginning of the universe. The Big Bang produced only hydrogen, helium, and trace amounts of lithium. Everything heavier, every atom of carbon in your body, every molecule of oxygen you breathe, every atom of iron in your blood, was created inside stars through nuclear fusion. When massive stars exhaust their nuclear fuel and explode as supernovae, they scatter these newly forged heavy elements into space, enriching the interstellar medium. Subsequent generations of stars form from this enriched gas, and with them come planets rich in heavy elements. The presence of these elements in Andromeda means the galaxy has hosted many generations of stars over its 10 billion year history, each generation living, enriching the cosmos, and passing away to make room for the next. Astronomers have also discovered planets in the Andromeda galaxy, though detecting them is extraordinarily challenging given the distance. In 2009, researchers announced the discovery of a planet orbiting a star in Andromeda, detected through a technique called microlensing. This planet is massive, about 6 times the size of Jupiter, suggesting it is a gas giant with no solid surface, certainly nothing that could support life as we know it. But where there is one planet, there are likely many more. With 1 trillion stars in Andromeda, the galaxy almost certainly hosts countless planetary systems, perhaps hundreds of billions of planets total. Some will be rocky worlds like Earth, orbiting in the habitable zones of their stars where liquid water can exist. Whether any of these planets harbor life is one of the great unanswered questions of our time. But the sheer numbers make it seem almost inevitable. The study of Andromeda has been crucial for understanding galaxies in general. Because we live inside the Milky Way, much of our own galaxy is obscured from view by interstellar dust. It is like trying to map a forest while standing in the middle of it. Trees block your view in every direction. But Andromeda, lying outside our galaxy, can be observed in its entirety. By studying Andromeda, astronomers learn about spiral galaxy structure, evolution, star formation, and dynamics in ways that would be impossible studying the Milky Way alone. Andromeda serves as a proxy, a stand-in, teaching us about galaxies across the universe. The Andromeda Galaxy has been imaged by nearly every major telescope and space observatory. The Hubble Space Telescope captured the largest astronomical photograph ever assembled, a mosaic of Andromeda containing over 1 billion pixels and revealing more than 100 million individual stars. This image required over 7,000 individual exposures, taken over 411 separate pointings of the telescope. The level of detail is breathtaking. You can see individual stars spread across 61,000 light-years of the galaxy's disk, like photographing a beach and resolving individual grains of sand. The Spitzer Space Telescope, which observed in infrared wavelengths, revealed Andromeda's dust and the cooler stellar populations, showing the galaxy's underlying skeletal structure. The Chandra X-ray Observatory identified dozens of black hole candidates in Andromeda. Stellar mass black holes formed from the collapse of massive stars, now accreting matter from companion stars and emitting intense X-rays. Ground-based radio telescopes have mapped the distribution of neutral hydrogen gas, revealing how it is displaced from the stellar disk by interactions with satellite galaxies. Let your mind wander now through Andromeda's neighborhoods. Imagine floating in space above the galaxy, watching it slowly rotate. You see the central bulge, that bright spherical concentration of old yellow stars packed densely together, orbiting the supermassive black hole in the core. Moving outward, you encounter the disk, a vast flattened plain of stars, gas, and dust, spiraling in graceful arms, punctuated by bright knots of star formation. Young, hot blue stars illuminate nebulae in shades of crimson and azure. Dark lanes of dust thread through the disk like cosmic rivers. Farther out still, you reach the halo, a spherical region sparsely populated by old, solitary stars, ancient globular clusters. The halo extends far beyond the visible disk, a ghostly, tenuous envelope that fades imperceptibly into the intergalactic medium. Andromeda moves through space, not alone, but as part of a gravitationally bound collection called the Local Group. This is our cosmic neighborhood, a cluster of more than 100 galaxies spread across about 10 million light-years. The Local Group is dominated by two giants, the Milky Way and Andromeda, with all the other members being dwarf galaxies, small and faint by comparison. The third largest member, the Triangulum Galaxy, sometimes called M33, is about 10 times smaller than Andromeda, and may actually be a satellite of Andromeda, gravitationally bound and orbiting the larger galaxy over timescales of billions of years. Together, these galaxies form a cosmic ecosystem, interacting through gravity, exchanging matter through tidal streams, and shaping each other's evolution. When you look at Andromeda in the night sky, you are engaging in an act that connects you to the entire history of human curiosity. Persian astronomers saw it more than 1,000 years ago. Medieval scholars pondered its nature. Early telescopic observers marveled at its structure without understanding what they were seeing. Edwin Hubble's revelation that it was a separate galaxy fundamentally changed humanity's place in the cosmos. We are not residents of the universe. We are residents of a galaxy, one of hundreds of billions scattered through space. Andromeda reminds us of both our insignificance and our potential. We are tiny, fragile creatures living on a small world orbiting an ordinary star. But we are also beings capable of understanding the cosmos, of reaching out with our minds and instruments to touch galaxies millions of light years away. There is something deeply soothing about contemplating such vastness. In the face of Andromeda's trillion stars and 10 billion-year history, your daily worries shrink to their proper size. The universe is ancient and enormous, filled with wonders beyond counting. You are a part of this universe, made of atoms forged in stars long ago. Atoms that were once inside other galaxies, other star systems, before finding their way here to Earth and into you. You are literally made of stardust, as the astronomer Carl Sagan famously said. When you look at Andromeda, you are looking at family, distant cousins in the cosmic sense, stars and worlds born from the same primordial material that coalesced into our solar system. Recent observations continue to reveal new surprises about Andromeda. Astronomers have found that some massive stars in Andromeda skip the supernova phase entirely and collapse directly into black holes in what are called failed supernovae. Instead of exploding brilliantly, these stars simply wink out of existence, their outer layers falling inward to join the collapsing core. One such event, designated M31 2014-DS1, was observed when a massive star simply vanished from view. Roughly 98% of its mass collapsed inward, forming a black hole about 6.5 times the mass of the Sun. Failed supernovae may account for 20 to 30% of massive star outcomes, but they are difficult to observe precisely because they do not produce bright explosions. Andromeda's magnetic field has also been mapped using radio telescopes. Ordered magnetic fields run along the galaxy's 10 kiloparsec ring, the prominent structure of gas and star formation, roughly 32,000 light-years from the center. These magnetic fields, though incredibly weak by everyday standards, play crucial roles in shaping the interstellar medium, guiding charged particles, and influencing star formation. The fields are generated by the motion of charged particles in the galaxy's disk, creating a cosmic dynamo effect, similar to how Earth's magnetic field is generated by motion in our planet's liquid iron core. Andromeda is also a laboratory for studying dark matter, the mysterious, invisible substance that makes up most of the matter in the universe. We cannot see dark matter directly because it does not emit, absorb, or reflect light. We know it exists only through its gravitational effects on visible matter. Andromeda is surrounded by an enormous dark matter halo, an invisible cloud of this mysterious substance extending far beyond the visible galaxy. The dark matter halo contains several times more mass than all the stars, gas, and dust in the galaxy combined. When the Milky Way and Andromeda eventually interact, their dark matter halos will play a crucial role in determining the outcome, influencing the orbital dynamics through gravitational friction. Imagine now that you are floating beside Andromeda, close enough to resolve individual stars. Below you stretches an endless ocean of suns, each one distinct, each one a story. Here, a young star cluster has just been born, dozens of blue giants blazing fiercely, their combined light ionizing the surrounding nebula into glowing red arcs. There, a red supergiant nears the end of its life, swollen to hundreds of times the Sun's diameter, its outer layers puffing away into space in a slow, majestic departure. Beyond it, a white dwarf, the collapsed core of a star that long ago shed its outer envelope, now cooling slowly over trillions of years. A pulsar spins thousands of times per second, its beam of radiation sweeping across space like a cosmic lighthouse. A binary system, two stars locked in mutual orbit, exchanges mass in a delicate gravitational dance that will eventually lead one or both to catastrophic ends. The diversity is staggering, each star system unique, each following its own evolutionary path. Andromeda's future is intertwined with our own. Whether the galaxies collide in 4 billion years or continue their orbital waltz for longer, their eventual merger is highly probable given enough time. When it happens, assuming any observers still exist in either galaxy, the night sky will transform over millions of years. First, Andromeda will grow larger and larger in the sky, eventually spanning horizon to horizon like a cosmic rainbow. The two galaxies will interpenetrate, passing through each other in a ghostly, slow-motion collision. Stars will be flung in all directions. The sky will light up with newly formed stars, thousands of new bright points appearing over the course of millennia. Supernovae will flash like cosmic fireworks. The combined light of the merging galaxies will briefly rival entire galaxy clusters. And then, slowly, over hundreds of millions of years, the chaos will settle. The merged galaxy will relax into a stable elliptical configuration, its star formation exhausted, its gas and dust mostly consumed or expelled. The remaining stars will orbit peacefully in a vast, diffuse cloud, and the night sky, for any worlds still capable of hosting observers, will be filled with a soft, even glow, the light of trillions of stars blended together into a gentle luminosity. But tonight, Andromeda remains what it has been for billions of years, a magnificent spiral galaxy, our closest large neighbor, a beacon in the darkness. When you go outside after listening to this, find a dark spot, let your eyes adjust, and look for that faint smudge in Andromeda's constellation. Remember that you are seeing light that left that galaxy when our ancestors were still learning to walk upright, when the world was younger and humanity had not yet dreamed of reaching the stars. That light has traveled unimaginably far just to reach you, crossing the empty void for more than 2 million years, surviving the journey intact to tell you one simple truth. You are part of something vast and beautiful and ancient. You are connected to the cosmos in ways that go beyond words. The universe is not a cold, dead place. It is alive with light and motion, with galaxies dancing through space, with stars being born and passing away, with planets forming and evolving, with the possibility of life scattered across billions of worlds. Andromeda is one chapter in this grand story, and so are you. Your atoms came from stars. Your thoughts are the universe becoming aware of itself. When you gaze at Andromeda, the galaxy gazes back through you, matter contemplating matter, consciousness recognizing its cosmic heritage. Let yourself feel small tonight, but also feel connected. You are a temporary pattern in the endless flow of matter and energy, but you are also a pattern capable of wonder, of curiosity, of love. The same fundamental forces that hold Andromeda together, that guide its stars in their orbits, that govern its black holes and nebulae, also hold you together, guide your thoughts, govern the chemistry of your cells. There is no separation between you and the cosmos. You are made of the cosmos. You are a way for the universe to know itself, as Carl Sagan said. Andromeda is a mirror, showing you not just a distant galaxy, but your own origins written in starlight. The light from Andromeda carries with it information about the galaxy's motion, composition, and history. When astronomers split this light through a spectrograph, spreading it out like a rainbow, they can read the chemical fingerprints embedded within. Each element, when heated, produces a unique pattern of bright or dark lines at specific wavelengths. Hydrogen produces its characteristic series of lines. Helium adds its own signature. Carbon, nitrogen, oxygen, iron, and dozens of other elements each contribute their unique spectral markings. By analyzing these patterns, astronomers can determine not just what Andromeda is made of, but also how its stars are moving, whether they are approaching or receding, how fast they are rotating. The spectrum reveals temperature, pressure, magnetic field strength, and age. Every photon is a messenger carrying news from across the cosmic ocean. One of the remarkable things about observing Andromeda is that we can see it in so many different wavelengths of light. Our eyes detect only visible light, that narrow slice of the electromagnetic spectrum ranging from red to violet. But the universe speaks in many voices, and Andromeda sings across the entire spectrum. In radio wavelengths, radio telescopes reveal vast clouds of neutral hydrogen gas distributed throughout the galaxy's disk. This hydrogen is the raw material for future star formation, cold and dark in visible light, but glowing brightly at the specific radio wavelength of 21 centimeters. The distribution of this hydrogen is not uniform. It shows gaps and holes where stars have already formed, consuming or dispersing the gas. It shows concentrations where future stars will be born. The hydrogen extends far beyond the visible disk, tracing the galaxy's full extent. In infrared wavelengths, Andromeda reveals its cooler components. The Spitzer Space Telescope, which observed entirely in infrared light, captured stunning images showing the galaxy's dust lanes glowing warmly. Infrared light penetrates dust clouds that block visible light, allowing astronomers to peer into star-forming regions and see newborn stars still wrapped in their natal cocoons. The infrared view also highlights older, cooler stars, the red giants and red dwarfs that populate the galaxy's older stellar populations. When you look at Andromeda in infrared, you see its thermal structure, the heat signatures of different regions, revealing patterns invisible to optical telescopes. In ultraviolet wavelengths, the hottest and youngest stars dominate. The Hubble Space Telescope, equipped with ultraviolet detectors, can observe the galaxy's most massive stars, those blue supergiants that burn so hot their surfaces reach temperatures of 30,000 degrees or more. These stars pour out most of their energy in ultraviolet wavelengths, invisible to our eyes but captured beautifully by space telescopes above Earth's atmosphere, which blocks most ultraviolet light. The ultraviolet view of Andromeda is a map of vigorous youth, showing where star formation is most active, where massive stars cluster together, where stellar winds and radiation pressure sculpt the surrounding gas into intricate patterns. In X-ray wavelengths, observed by telescopes like Chandra, Andromeda reveals its most violent and energetic phenomena. X-rays come from extremely hot gas, often millions of degrees, heated by shock waves from supernova explosions, or by material falling into black holes and neutron stars. The Chandra observations have identified dozens of X-ray sources in Andromeda, including stellar mass black holes accreting matter from companion stars, neutron stars in binary systems, supernova remnants still glowing from explosions that occurred thousands of years ago, and the faint X-ray glow from the supermassive black hole at the galaxy's center. Each X-ray source tells a story of extreme physics, of matter compressed and heated to conditions we can barely replicate in our most powerful laboratories. Even in gamma rays, the highest energy form of light, Andromeda has been detected. Gamma rays come from the most energetic processes in the universe: matter-antimatter annihilation, ultra-relativistic particles spiraling in magnetic fields, cosmic ray collisions with gas. The gamma-ray emission from Andromeda is faint, but it reveals the presence of cosmic rays, high-energy particles accelerated by supernova shockwaves and other violent events, coursing through the galaxy at nearly the speed of light. The study of Andromeda has revealed fascinating details about how galaxies evolve over cosmic time. Galaxies are not static objects, formed once and frozen forever. They are dynamic systems that grow through mergers and accretion, that form stars in bursts and lulls, that develop structure through complex gravitational interactions. Andromeda's current state is a snapshot in a billions of years long evolution. 10 billion years ago, when the galaxy first formed from the gravitational collapse of a large cloud of primordial gas, it would have looked very different. It was probably smaller, more chaotic, actively forming its first generation of stars from metal-poor gas. Over time, those stars enriched the interstellar medium with heavy elements. Subsequent generations formed from progressively richer material. The galaxy experienced periods of intense star formation, periods of relative quiescence, periods of violent mergers with other galaxies. Each merger added stars and gas, triggering new bursts of star formation, reshaping the galaxy's structure. The major merger, 2 to 3 billion years ago, was transformative, but it was likely not the first or the last. Andromeda has consumed dozens of smaller galaxies over its lifetime, each one adding to its mass and complexity. The stellar streams visible in its halo are the archaeological remains of these ancient meals, fossils of galaxies that no longer exist as distinct entities but live on as scattered stars in Andromeda's outskirts. Theoretical models of galaxy formation suggest that large spiral galaxies like Andromeda form through a hierarchical process. Small dark matter halos collapse first, pulling in gas that cools and forms the first stars. These small systems then merge to form progressively larger systems. Over billions of years, countless mergers build up galaxies like Andromeda. The process is messy and chaotic, driven by the invisible hand of dark matter gravity. The dark matter provides the gravitational scaffolding upon which visible matter accumulates. Without dark matter, galaxies as we know them could not exist. There would not be enough gravity to hold them together, or to accumulate enough mass to form in the first place. Consider the scale of structure in the universe. Andromeda and the Milky Way are just 2 galaxies in the local group, which itself is just a small cluster in the much larger Virgo supercluster, a vast collection of galaxy groups and clusters spanning about 110 million light-years. The Virgo supercluster, in turn, is part of an even larger structure called Laniakea, a supercluster of superclusters containing about 100,000 galaxies. And Laniakea is just one of countless such structures scattered throughout the observable universe, which extends about 46 billion light-years in every direction, containing perhaps 2 trillion galaxies. Andromeda, despite its grandeur, is one ordinary galaxy among trillions. Yet it is our neighbor, close enough to study in detail, close enough to see individual stars, close enough to feel almost intimate, despite the vast gulf separating us. The rotation curve of Andromeda has been a crucial piece of evidence in understanding dark matter. When astronomers measure how fast stars and gas orbit at different distances from the galaxy's center, they can calculate the distribution of mass. According to Newton's laws, if most of the mass were concentrated in the bright central bulge, stars farther out should orbit more slowly, just as planets farther from the Sun orbit more slowly than planets closer in. But that is not what we observe. Instead, the rotation velocity stays roughly constant, or even increases slightly as you move outward through the disk. This flat rotation curve implies that there is much more mass than we can see, distributed in a large halo extending far beyond the visible galaxy. This invisible mass is dark matter, and it outweighs the visible stars, gas, and dust by a factor of 5 or more. The same pattern is seen in galaxy after galaxy, providing compelling evidence that dark matter is real and that it plays a dominant role in the structure of the universe. Let us talk about the individual stars in Andromeda. Each one is a nuclear furnace, converting hydrogen into helium through the process of nuclear fusion. In the cores of stars, temperatures reach millions of degrees, and pressures are so extreme that hydrogen nuclei overcome their mutual electrical repulsion and fuse together, releasing tremendous energy in the process. This energy flows outward, eventually radiating away as light and heat from the star's surface. A star is a delicate balance between gravity trying to crush it inward and radiation pressure pushing outward. This balance can last for billions of years in stars like our Sun, or for only a few million years in the most massive stars that burn through their fuel at prodigious rates. The variety of stars in Andromeda is staggering. Red dwarfs, the smallest and coolest stars, make up the majority of the stellar population. These dim, cool stars have masses less than half that of the Sun and can burn steadily for trillions of years, far longer than the current age of the universe. They are so faint that even though they are the most common stars, they contribute little to the galaxy's overall brightness. Sun-like yellow dwarfs occupy the middle ground, moderate in size and temperature, burning their fuel at a steady rate that allows them to shine for about 10 billion years. Our Sun is about halfway through its life, still calmly fusing hydrogen in its core, still warming Earth and the other planets. Red giants are stars in the late stages of their evolution. They have exhausted the hydrogen in their cores and begun fusing helium into heavier elements. As they do so, their outer layers expand dramatically, swelling to hundreds of times their original size. These bloated stars are cool on their surfaces, glowing red but immensely bright because of their enormous surface area. In a few billion years, our Sun will become a red giant, expanding to perhaps engulf Mercury and Venus, and possibly Earth as well. Blue giants and blue supergiants are the most massive stars, with masses 10, 20, even 100 times that of the Sun. They burn incredibly hot and bright, pouring out more energy in a single day than the Sun releases in a century. But their profligate energy expenditure means they live fast and perish young, exploding as supernovae after only a few million years. White dwarfs are the remnants of stars like the Sun, the collapsed cores left behind after the star sheds its outer layers. A white dwarf is roughly the size of Earth, but contains as much mass as the Sun, making it incredibly dense. A teaspoon of white dwarf material would weigh several tons on Earth. White dwarfs no longer undergo nuclear fusion. They simply cool slowly over trillions of years, gradually fading from white to yellow to red to brown to black. Neutron stars are even more extreme. The collapsed cores of massive stars that exploded as supernovae. A neutron star is only about 12 miles across, but contains more mass than the Sun, compressed to such density that protons and electrons are crushed together into neutrons. A teaspoon of neutron star material would weigh as much as a mountain. Some neutron stars spin hundreds of times per second, their intense magnetic fields generating beams of radiation that sweep across space like lighthouse beams, creating the pulsing signals we detect as pulsars. Black holes represent the ultimate endpoint of stellar evolution for the most massive stars. When a star with a mass many times that of the Sun exhausts its nuclear fuel and collapses, no force can stop the implosion. The core collapses past the neutron star stage, shrinking to a point of infinite density called a singularity, surrounded by an event horizon the boundary beyond which nothing, not even light, can escape. Black holes are not cosmic vacuum cleaners, despite popular misconceptions. They do not suck in everything around them. If the Sun were suddenly replaced by a black hole of the same mass, Earth would continue orbiting exactly as before. The gravitational pull at Earth's distance would be unchanged. Black holes only exert exotic effects very close to the event horizon, where space-time is severely warped and tidal forces become extreme. The globular clusters orbiting Andromeda are among the most fascinating objects in the galaxy. These ancient stellar cities contain hundreds of thousands or even millions of stars packed into spherical volumes only tens of light years across. The stars in a globular cluster are so close together that in the cluster's core, the average distance between stars might be only a tenth of a light year, compared to the 4 light years separating the Sun from its nearest neighbor. If you lived on a planet orbiting a star in the core of a globular cluster, your night sky would be spectacular, filled with thousands of stars brighter than Sirius, the brightest star in Earth's sky. There would be no true night, only a perpetual twilight from the combined glow of nearby stars. Globular clusters are laboratories for studying stellar evolution. Because all the stars in a cluster formed at essentially the same time from the same gas cloud, they have the same age and the same initial chemical composition. The only thing that differs is their initial mass. This makes globular clusters ideal for testing theories of how stars evolve. The most massive stars have long since exhausted their fuel and perished, leaving behind white dwarfs, neutron stars, or black holes. The stars that remain are lower mass stars, still fusing hydrogen or helium in their cores. By observing which stars are present and which are absent, astronomers can determine the cluster's age and refine their understanding of stellar physics. The open star clusters in Andromeda are younger and less tightly bound than globular clusters. These clusters form in the spiral arms from collapsing molecular clouds, grouping dozens to thousands of stars together in loose associations. Over time, gravitational interactions with passing clouds and other stars disrupt the clusters, and the stars gradually disperse into the general stellar population. Most open clusters survive for only a few 100 million years before dissolving. The youngest open clusters still glow with the brilliant blue light of massive, short-lived stars. These hot stars illuminate the surrounding gas, creating colorful nebulae that mark active star-forming regions. Nebulae in Andromeda come in several varieties. Emission nebulae glow with the red light of hydrogen excited by ultraviolet radiation from nearby hot stars. The classic example in our own galaxy is the Orion Nebula. But Andromeda hosts countless such regions scattered throughout its spiral arms. Reflection nebulae shine with reflected starlight, their blue color coming from the same scattering process that makes Earth's sky blue. Dust particles scatter short wavelength blue light more efficiently than long wavelength red light, so starlight passing through dusty regions takes on a characteristic blue hue. Dark nebulae are dense clouds of dust and gas that block light from background stars, appearing as dark patches against the brighter background. These are often sites of future star formation, cold and dense enough for gravity to eventually overcome internal pressure and trigger collapse. Planetary nebulae, despite their name, have nothing to do with planets. They are the glowing shells of gas expelled by dying sun-like stars in their final stages of evolution. As a star runs out of hydrogen and helium fuel, it begins to pulsate, shedding its outer layers in a series of gentle eruptions. The exposed hot core, a white dwarf in the making, floods the ejected gas with ultraviolet radiation, causing it to glow in beautiful colors. These nebulae are short-lived by cosmic standards, lasting only 10,000 to 20,000 years before dispersing into the interstellar medium. Andromeda contains thousands of planetary nebulae, each marking the transformation of a star from active fusion to slow cooling. Supernova remnants are the expanding clouds of debris left behind by stellar explosions. When a massive star explodes as a supernova, it ejects most of its mass at velocities of 10,000 kilometers per second or more. This ejected material slams into the surrounding interstellar gas, creating a shockwave that heats the gas to millions of degrees. The remnant glows brilliantly in X-rays and radio waves, marking the site of one of the universe's most violent events. Over thousands of years, the remnant gradually cools and fades, mixing its enriched material with the interstellar medium, seeding future generations of stars with heavy elements. Supernovae are the primary source of elements heavier than iron. Gold, platinum, uranium, and all the other heavy elements that we value and use were created in supernova explosions and neutron star mergers, then scattered into space to be incorporated into later solar systems. The interstellar medium in Andromeda, the gas and dust between the stars, is not empty space, but a rich, complex environment. It contains mostly hydrogen and helium, the primordial elements from the Big Bang, but also substantial quantities of heavier elements synthesized in stars and expelled into space. The gas exists in several phases with different temperatures and densities. Cold molecular clouds, with temperatures of only 10 to 20 degrees above absolute zero, are the densest regions, where hydrogen molecules clump together and shield themselves from starlight. These clouds are the nurseries where new stars form. Warm, neutral hydrogen, at temperatures of a few thousand degrees, makes up much of the interstellar medium, filling the spaces between stars and clouds. Hot, ionized gas, heated to millions of degrees by supernova shockwaves and stellar winds, fills vast, low-density regions and emits X-rays. Cosmic rays, high-energy particles accelerated to nearly the speed of light, permeate the interstellar medium. These particles, mostly protons but also heavier atomic nuclei and electrons, spiral along magnetic field lines, filling the galaxy with invisible, high-energy radiation. When cosmic rays collide with gas atoms, they can produce secondary particles, including gamma rays, the highest energy form of light. Cosmic rays also affect star formation by providing pressure that helps support molecular clouds against gravitational collapse. Understanding cosmic rays is crucial for understanding the energy balance and dynamics of the interstellar medium. Magnetic fields thread through Andromeda's disk and halo, though they are incredibly weak by everyday standards, about 1 million times weaker than Earth's magnetic field. Despite their weakness, these magnetic fields play important roles. They guide the motion of charged particles, confine cosmic rays, affect the collapse of gas clouds, and influence the structure of the interstellar medium. The fields are generated by dynamo processes, the same type of mechanism that generates Earth's magnetic field, but operating on a galactic scale. The rotation of the galaxy and the motions of ionized gas create electric currents that generate and amplify magnetic fields. These fields can be mapped using radio telescopes that detect the polarization of radio waves emitted by the galaxy. The process of star formation in Andromeda follows the same basic principles as star formation everywhere in the universe. It begins with a cold, dense molecular cloud, a region where gravity is strong enough to overcome the internal pressure of the gas. Something triggers the collapse, perhaps the shock wave from a nearby supernova, perhaps a collision with another cloud, perhaps simply random fluctuations in density. Once collapse begins, gravity takes over. The cloud fragments into smaller clumps, each of which continues to collapse. As a clump shrinks, it heats up. Eventually, the center becomes hot and dense enough for nuclear fusion to ignite. A star is born. The process is messy, inefficient. Only a small fraction of the cloud's mass ends up in stars. The rest is blown away by stellar winds and radiation pressure from the newly formed stars. Stars typically form in groups, sometimes dozens or hundreds at once from the same parent cloud. The most massive stars form first and evolve rapidly, exploding as supernovae, while their lower mass siblings are still settling onto the main sequence. These explosions can trigger further star formation by compressing nearby gas clouds, creating a cascade of star formation that sweeps through a region over millions of years. Eventually, the stellar winds and supernova explosions disperse the remaining gas, and star formation ceases until new clouds accumulate. The chemical evolution of Andromeda has progressed over billions of years. The first stars, formed from primordial gas containing only hydrogen and helium, were different from stars today. They were probably more massive on average, burning hotter and faster, quickly enriching their surroundings with heavier elements. Each subsequent generation of stars formed from slightly enriched gas, incorporating the products of previous stellar life cycles. This process, called galactic chemical evolution, gradually increased the abundance of heavy elements in the galaxy. Today, stars forming in Andromeda have chemical compositions similar to the Sun, with a few % of their mass in elements heavier than helium. This enrichment has profound implications. It makes possible the formation of rocky planets, the chemistry of life, and the complex molecules we observe in space. The ages of stars in Andromeda span the galaxy's entire history. The oldest stars, found primarily in the halo and the central bulge, are nearly as old as the universe itself, perhaps 10 to 12 billion years old. These ancient stars formed when the galaxy was young, and they have witnessed the entire subsequent history of galactic evolution. The disk contains a mix of ages, with older stars in the thick disk and younger stars in the thin disk. The spiral arms are dominated by young stars, formed within the last few 100 million years. The continuous presence of star formation means that Andromeda, unlike elliptical galaxies that have exhausted their gas supplies, remains a living, evolving system. When you contemplate Andromeda, you are contemplating time as much as space. The light you see left the galaxy 2.5 million years ago. If someone in Andromeda were looking back at Earth right now, with a sufficiently powerful telescope, they would not see modern civilization. They would see Earth as it was 2.5 million years ago, in the early Pleistocene epoch, when early humans first appeared in Africa, when the continents were locked in ice ages, when mammoths and saber-toothed cats roamed the land. There is a profound disconnect between our perception of now and the reality of cosmic distances. Every observation of a distant object is an observation into the past. Astronomy is a form of time travel, allowing us to witness events that occurred millions or billions of years ago. Light that has been traveling through space for eons, carrying information about conditions long before Earth even existed. This time delay also means that if something dramatic happened in Andromeda today, we would not know about it for 2.5 million years. If the supermassive black hole suddenly became active, if a supernova exploded, if a massive star formation burst began, the light from those events would not reach us until the distant future. Conversely, anything we observe happening in Andromeda now actually happened in the distant past. The galaxy we see is a ghost, an image of how things were, not how they are. This is true for all astronomical observations. The farther we look, the farther back in time we see. Distant galaxies, billions of light years away, show us the universe as it was billions of years ago, when it was younger, denser, more active, and fundamentally different from the universe we inhabit today. The concept of distance itself becomes complex on cosmic scales. The 2.5 million light-years to Andromeda is a proper distance, the distance you would measure if you could freeze the expansion of the universe and stretch a tape measure from here to there. But the universe has been expanding during the time the light has been traveling, so the actual space the light has crossed is different from the current distance. For nearby objects like Andromeda, the difference is negligible. But for very distant galaxies, the expansion becomes significant. Light from the most distant galaxies has been traveling for over 13 billion years, but those galaxies are now over 46 billion light-years away, because space itself has been stretching during the journey. Let your mind rest now on the simple wonder of Andromeda's existence. 2.5 million light-years away, 1 trillion stars orbit a common center. Planets circle those stars. Moons orbit those planets. Asteroids tumble through the darkness. Comets swing through the outer reaches on long elliptical paths. Gas clouds collapse to form new stars. Old stars expire in final brilliance or quiet fading. Black holes lurk, warping space-time. Pulsars spin, flashing their beams into the void. And through it all, gravity holds everything together, the fundamental force that shapes the cosmos. For those who wish to observe Andromeda with their own eyes, the experience connects you directly to this cosmic wonder in a way that no photograph or description can match. Finding Andromeda is surprisingly easy once you know where to look. The best time to observe is during autumn in the Northern Hemisphere, from September through February, when the constellation Andromeda rides high overhead during evening hours. Start by locating the Great Square of Pegasus, 4 bright stars forming a large square in the southern sky. From the northeastern corner of the square, a line of 3 bright stars extends to the northeast. These are the main stars of Andromeda. Follow this chain, and about halfway along, you will find a fainter star. From this star, a smaller chain of stars branches off perpendicular to the main line. If you look just above this branch, in a dark sky free from light pollution, you should see a faint, fuzzy oval patch. That is Andromeda, appearing as a soft glow against the darkness. Alternatively, you can use Cassiopeia as a guide. This distinctive W-shaped constellation is easy to spot in the northern sky. The brightest star in Cassiopeia, Shedar, points almost directly toward Andromeda. If you draw an imaginary line from Shedar southward, it leads you straight to the galaxy. On a truly dark night, far from city lights, Andromeda is visible as an elongated smudge about 3 times the width of the full moon. It appears faint because its light is spread over such a large area, but it is unmistakable once you know what you are looking for. Binoculars greatly enhance the view, revealing the galaxy's elliptical shape and its bright central core. With binoculars, you might also spot the 2 companion galaxies, M32 and M110, appearing as small, faint patches near the main galaxy. A small telescope reveals even more detail. The dark dust lane on the northwestern edge of the core, bright star clouds in the disk, and a more pronounced oval shape. Larger telescopes, 8 inches or more in aperture, can show faint details in the spiral structure, though seeing these details requires dark skies, patience, and the technique of averted vision. where you look slightly to the side of the object to take advantage of the more sensitive parts of your retina. Astrophotographers have captured breathtaking images of Andromeda, revealing details invisible to the eye. Long exposures with sensitive cameras accumulate light over minutes or hours, bringing out faint structures, colors, and details. The photographs show the galaxy in its full glory. The bright yellow-orange central bulge, the blue spiral arms dotted with pink nebulae, the dark dust lanes threading through the disk, and the faint outer halo fading gradually into the darkness. Modern digital cameras and processing techniques have made astrophotography accessible to amateurs, and countless enthusiasts around the world have captured stunning images of Andromeda from their backyards. Professional observatories have pushed the boundaries of what we can see in Andromeda. The Hubble Space Telescope's mosaic of the galaxy, assembled from thousands of individual images, contains over 1 billion pixels and shows more than 100 million individual stars. Zooming into this image is like exploring an alien landscape. You can see individual stars of different colors and brightness, star clusters containing dozens or hundreds of stars, nebulae glowing in shades of red and blue, and dark dust clouds silhouetted against brighter backgrounds. The image spans 61,000 light-years, capturing a section of the galaxy's disk in unprecedented detail. It is a humbling reminder that what appears as a small, fuzzy patch in the night sky is actually an entire universe unto itself, containing complexity and diversity beyond our ability to fully comprehend. The discovery that Andromeda is approaching us rather than receding came as a surprise to early astronomers. Most galaxies in the universe are moving away from us, their light stretched to longer wavelengths by the expansion of space itself, a phenomenon called redshift. But Andromeda shows blue shift, meaning its light is compressed to shorter wavelengths because the galaxy is approaching. This is possible because the local motion of Andromeda toward the Milky Way, driven by mutual gravitational attraction, is stronger than the expansion of space over such a relatively short distance. The local group of galaxies is gravitationally bound, meaning the galaxies are held together by their mutual gravity, overcoming the cosmic expansion. On larger scales, beyond the local group, the expansion dominates and nearly all galaxies are receding from us. The measurement of Andromeda's sideways motion across the sky, its proper motion, required extraordinary precision. Even though the galaxy is racing toward us at over 100 kilometers per second, its sideways motion as seen from Earth is incredibly small because of the enormous distance. The Hubble Space Telescope measured this motion by observing the positions of stars in Andromeda in 2002 and again in 2010, comparing their positions relative to distant background galaxies that serve as fixed reference points. By averaging over thousands of stars, astronomers achieved the precision necessary to detect motion of less than 1/10,000th of an arcsecond per year. An arcsecond is 1/3600th of a degree, and 1/10,000th of an arcsecond is an angle so small it is almost incomprehensible. It would be like detecting the width of a human hair from 50 miles away. This precision allowed astronomers to predict the future trajectory of Andromeda with reasonable confidence, though uncertainties remain. The galaxy's path depends not just on its current motion, but also on the distribution of dark matter in both galaxies, the gravitational influence of other nearby galaxies, and subtle effects we may not yet fully understand. The recent revision of the collision probability from near certainty to roughly 50-50 demonstrates how ongoing observations and refined calculations can change our understanding. Science is a self-correcting process, always refining its models as new data becomes available. Imagine standing in a field on a crisp autumn night, your breath misting in the cold air, looking up at Andromeda. You are seeing light that left the galaxy when our ancestors were just beginning to walk upright, when Homo habilis was crafting the first stone tools in East Africa, when the world was in the grip of the Pleistocene ice ages. The photons entering your eyes have been traveling through empty space for 2.5 million years, maintaining their journey without pause, without deviation, crossing the vast gulf between galaxies. They passed through clouds of intergalactic gas, survived encounters with dust grains, traversed the dark matter halos of both galaxies, and finally, after an epic journey spanning a significant fraction of our species' entire existence, they landed on your retina, triggering a cascade of chemical reactions that your brain interprets as a faint, fuzzy patch of light. This connection across time and space is profound. You are touching the past, seeing events that happened eons ago, participating in a cosmic conversation that spans the universe. Andromeda is speaking to you in the language of light, and you are listening. Every person who has ever looked up at that galaxy, from Persian astronomers 1,000 years ago to you tonight, has seen the same ancient light, has felt the same wonder, has contemplated the same cosmic vastness. The galaxy connects us all across time, a shared experience that transcends culture, language, and era. Consider the philosophical implications of Andromeda's existence. The galaxy demonstrates that Earth is not unique, that our Milky Way is not unique, that the universe is filled with countless other worlds and systems. The Copernican principle, the idea that Earth does not occupy a special place in the universe, is confirmed repeatedly by observations of galaxies like Andromeda. We are not at the center. We are not special in any cosmic sense. We are ordinary, one planet around one star in one galaxy among trillions. This realization is simultaneously humbling and liberating. It diminishes our cosmic significance, but expands our vision of what is possible. If life arose here, in this unremarkable corner of an unremarkable galaxy, why not elsewhere? The universe is vast beyond measure, filled with opportunities for life to emerge, evolve, and perhaps even develop intelligence and civilization. The question of whether intelligent life exists in Andromeda is unanswerable with current technology, but we can speculate based on what we know. With 1 trillion stars, many likely hosting planets, the odds seem favorable that at least some worlds in Andromeda harbor life. Perhaps microbial life, simple organisms clinging to existence in harsh environments. Perhaps complex life, diverse ecosystems teeming with alien biology. Perhaps even intelligent life, beings capable of contemplating their own existence, wondering about their place in the cosmos, looking out at the Milky Way and wondering if anyone is looking back. If such beings exist, they see our galaxy as we see theirs, a faint, fuzzy patch in their night sky, a distant island of stars. Perhaps at this very moment, an alien astronomer in Andromeda is pointing their telescope at the Milky Way, studying its structure, measuring its motion, pondering the same questions we ponder about them. The vast distances between galaxies mean that any communication with hypothetical civilizations in Andromeda would be impractical. Even traveling at the speed of light, a message would take 2.5 million years to reach them, and another 2.5 million years for a reply to return. By the time we received a response, our civilization would likely have evolved or even perished, replaced by descendants unimaginably different from us, or possibly by no civilization at all. The timescales of interstellar and intergalactic communication dwarf human lifespans, and even human civilizations. Any meaningful dialogue across such distances would require patience measured not in lifetimes, but in geological epochs. Yet, the attempt might still be worthwhile, not for practical communication, but for the philosophical statement it makes. Sending a message to Andromeda would be an affirmation that we exist, that we care about the universe beyond our own world, that we are willing to reach out, despite the impossibility of seeing results in our lifetimes. It would be a gift to the future, both ours and theirs, a message in a bottle cast into the cosmic ocean, hoping that someday, somehow, someone will find it and know that they are not alone. Andromeda also serves as a laboratory for testing our theories of cosmology and physics. The galaxy's structure, motion, and evolution provide data points for understanding how the universe works. Observations of Andromeda have contributed to our understanding of dark matter, dark energy, galaxy formation, stellar evolution, and countless other topics. Each new observation, each new measurement, refines our models and expands our knowledge. Science is an iterative process of observation, hypothesis, testing, and revision. Andromeda has been central to this process for over a century, from Hubble's discovery of its true distance to recent measurements of its motion and structure. The future of Andromeda studies looks bright, with new telescopes and instruments coming online that will reveal even more about the galaxy. The James Webb Space Telescope, launched in late 2021, observes in infrared wavelengths and has already begun capturing stunning images of Andromeda with unprecedented sensitivity and resolution. Future extremely large telescopes, with mirrors 30 or 40 meters across, will be able to study individual stars in Andromeda in far greater detail than ever before. Space-based observatories, specializing in specific wavelengths, will continue to reveal different aspects of the galaxy's structure and behavior. Each new generation of instruments brings new discoveries, answering old questions and raising new ones. As you lie here tonight, drifting towards sleep, let Andromeda be your companion, the darkness. Let its ancient light be a comfort, a reminder that the universe is vast and beautiful, full of wonders waiting to be discovered. Let the knowledge that 1 trillion stars shine in that distant galaxy fill you with awe and peace. You are part of this universe, connected to everything in it through the fundamental forces of physics and the shared history of matter. The atoms in your body were once inside stars, perhaps in Andromeda, perhaps in the Milky Way, forged in nuclear furnaces and scattered into space to eventually find their way to Earth and into you. There is a meditation in astronomy, a contemplation of the infinite that puts our daily concerns into perspective. When you think about Andromeda, your worries seem small. Your problems, real and valid as they are to you, are fleeting blips in the cosmic timeline. The galaxy will still be there long after you are gone, shining its ancient light into the darkness, waiting for future generations to look up and wonder. This perspective is not meant to diminish your experiences, but to contextualize them, to remind you that you are part of something larger, that your existence is a brief but meaningful moment in the ongoing story of the universe. The cosmos is indifferent to our existence, yet we find meaning in it. We look up at the stars and see beauty. We study galaxies and feel wonder. We contemplate the vastness of space and time and find inspiration. This capacity for wonder, this ability to appreciate the universe, is perhaps one of humanity's greatest gifts. We are the universe's way of knowing itself, consciousness arising from matter to contemplate its own origins and destiny. When you look at Andromeda, you are the cosmos looking at itself, awareness examining awareness, existence pondering existence. As we draw this gentle journey to a close, let your breathing deepen and slow. Feel the weight of your body sinking into the comfort of your bed. The day's concerns are fading now, dissolving like morning mist under the light of 1,000,000,000,000 distant suns. Andromeda will still be there tomorrow night, and the night after, and for billions of nights to come. The universe is patient. The stars are eternal on human timescales. There is no rush, no urgency. Everything that needs to happen will happen in its own time, according to the laws written into the fabric of existence, billions of years before you were born. Close your eyes now, and let the darkness behind your eyelids become the darkness of space. Imagine yourself floating peacefully among the stars of Andromeda, surrounded by gentle light, held by gravity, safe in the vast emptiness. You are warm. You are comfortable. You are exactly where you need to be. The galaxy rotates slowly around you, a cosmic lullaby of light and motion, ancient and new at the same time, singing the song that all matter sings, the song of existence itself. You have done enough thinking for today. You have traveled far, across millions of light years, through time and space, learning about wonders that stretch the boundaries of imagination. Now it is time to let go. Let your thoughts drift away like leaves on a gentle stream. Let sleep come naturally, easily, without effort. Your body knows what to do. Your mind knows how to rest. The universe will keep turning without your attention. Andromeda will continue its slow dance through space. Stars will be born and perish. Galaxies will merge and separate. And you will sleep, peaceful and content, held by the same gravity that holds galaxies together, part of the same cosmos that created everything you see and know. The Andromeda galaxy is out there, shining in the darkness, a beacon of light in the cosmic ocean. And you are here, safe and warm, ready to rest. Let the knowledge of that distant galaxy comfort you. Let the vastness of space remind you that your problems are small and temporary. Let the ancient light from Andromeda's 1,000,000,000,000 stars be a blanket of peace wrapped around you, gentle and infinite. Sleep now. Dream of galaxies and stars, of cosmic collisions billions of years away, of worlds you will never see but can imagine. Dream of light traveling through emptiness, patient and eternal, carrying stories across the universe. Dream of connection and wonder, and the simple miracle of existence. You are part of something beautiful, something vast beyond measure. Rest in that knowledge. Rest in the quiet certainty that you belong here, in this moment, in this universe, under the watchful gaze of 1,000,000,000 galaxies. The Andromeda galaxy wishes you good night. The stars sing their ancient lullaby. And you, dear listener, can finally let go and drift into sleep, peaceful and whole, knowing that tomorrow the universe will still be there, waiting to share more of its secrets. But for now, only this moment matters, only this breath, only this peaceful descent into dreams. Sweet dreams, traveler. The cosmos holds you gently tonight. Rest well beneath the light of distant stars. You have done enough for today. Close your eyes, rest, and dream. Good night.